SwayamPrabha. Digital India. Educated India.
We give an input. Let's say, like you have a system, right? Like a black box. Let's say you have a signal generator. You give an ideal impulse input. Let's say you have a data logger at the system output terminal, right? You log the output. You get the output signal, right? You have the measurements. So that is the impulse response. Provided you can give an ideal impulse input, right? So that's the thing. Then you use the data to figure out the transfer function of the system. Okay? What we will do is that, like when you come towards the end of the semester, I will give you a project where we will give you real experimental data, okay, and you need to figure out the plant transfer function. Okay, we will do a small project, okay, which will essentially help you in learning how this can be done. All these aspects can be put to use. Okay, yeah. Okay, so now I am going to tell you something in general. In general, the governing equation of what we call as an nth order. See, the mass spring damper system was a second order system, right? Because the highest derivative of the output term was order 2, right? So, an nth order CISO LTI causal dynamic system can be written as, okay. So, in general, the governing equation of an nth order CISO LTI causal system can be written as the following, okay. So, A naught dny t dtn plus A1 dn minus 1 yt dtn minus 1 all the way till an minus 1 dy dt plus an y of t, okay. That is going to be equal to b naught dm ut dtm plus b1 dm minus 1 ut dtm minus 1 plus all the way till bm minus 1 du dt plus bm ut. Okay, so this is how in general the governing equation for the class of systems that we are going to study would come up. Okay, so please note that this class of systems, like is modeled by using a linear ODE with constant coefficient, right? So immediately you can see that it's a linear ODE, it's linear in y and u, okay, that is something which all of us can observe. It has constant coefficients, that is reflective of time invariance, okay. So let me write down all the implications, because just by looking at the equation you should be able to tell things about the system, right? What class of systems that we are looking at, like, so time invariance is reflected by the fact that we have constant coefficients, right, in the above equation, okay. So the fact that it's linear, because the above equation is linear in u of t and y of t and the derivatives of these variables, right, and causality is reflected by the fact that n is greater than or equal to m, okay. So when the highest order of the input term derivative, right, the highest derivative of the the output term y of t, right, n is the order of the highest derivative of y of t, right. So m is the order of the highest derivative of the input u of t. When n is greater than m or at the worst equal to m, you have a causal system, right? When n is greater than m, some people will call it a strictly causal. Okay, so I'm just introducing you to some terms which you may encounter. Right? So essentially, causality is reflected by the fact that n is greater than or equal to m. Okay, so that's how causality is reflected in this particular equation. Okay, so this is an nth order system where n is the order of the highest derivative of the output term. Okay, so for example, as an example, right, for the mass spring damper system, I know, like what were n and m. That we just considered, right? What were the values of n and m? If you look at the mass spring damper system, right? See, for the mass spring damper system, the input was the force f of t, right? The output was the displacement x of t, correct? So what was the value of n? 2, because we had x double dot. What about m? 0, because there was no derivative of the force term at all, right? On the right hand side we had just f of t, right? So immediately you see that n is greater than m. So that was a causal system, right? So that's a representation of a causal system. That means that before you give a force, the mass is not going to get displaced, right? So only the current displacement is going to depend on past and current force that you are giving to the system, right? That's a causal system. So that's how the as different aspects of LTA causality are reflected in the governing equation. Now this is something I'm going to leave it to you as a homework problem, because we did it in detail for the mass spring damper system. This is just a general case. Okay, so take the Laplace transform on both sides. Okay, and apply 0 initial conditions to obtain P of s to be equal to y of s divided by u of s, the Planck transfer function, which will turn out as b naught s power m plus b1 s power m minus 1 all the way till bm minus 1s plus bm divided by a naught s power n plus a1 s power n minus 1 all the way till a n minus 1s plus a n. Okay, so this I leave it as homework. Okay, so once again pretty straightforward. You just take the Laplace transform on both sides. If you apply all the initial conditions to be 0, when you take the Laplace transform of the nth derivative, the only term which will remain is s power n y of s. Similarly, when you take the Laplace transform of the n minus 1 derivative of y, if you apply all the initial conditions to be 0, the term which you will be left with is s power n minus 1 y of s. So that's what you will be left with. Same story in the right hand side, right? If you take the Laplace transform of the mth derivative of the input, you will have s power m u of s plus a bunch of terms having initial conditions of the input. Even that you take as 0, so you will be just left with s power m u of s. So you cross multiply, this is what you would get. Okay, so that's the Planck transfer function in this particular case. So that's what we have, okay, as the Planck transfer function. So immediately we will see, like what really is the consequence, right? So let's look at it further. So immediately one can observe that the Planck transfer function is a ratio of two polynomials in S, right? So one could say that like P of s is a ratio of two polynomials, n of s is by d of s, right? So n of s is the numerator polynomial of order, what is the order of the numerator polynomial? Of order m, right? Because the highest power is s power m term, right? So similarly, d of s is a denominator polynomial and that is of order n. Okay. So we see that the plant transfer function in general is going to be a ratio of two polynomials in S, a numerator polynomial and a denominator polynomial. Okay. So for when n is greater than or equal to m for a causal system, we are going to have what is called as a proper transfer function. Okay, transfer function is said to be proper when the ratio of the when the order of the denominator polynomial is greater than or equal to the order of the numerator polynomial. Okay, and in this case anyway we are dealing with causal systems, that's going to be true. Okay, so for the class of systems that we are going to deal with, we are going to get proper transfer functions. Okay, so when n is strictly greater than m, we add the term strictly. Okay, like we are going to get what is called as a strictly proper transfer function. Okay, that's what is going to result when n is strictly greater than m. Okay, so that's essentially a definition of what is called as a proper transfer function and a strictly proper transfer function. Okay, so now we see that P of s is going to be equal to n of s divided by d of s, right? So we see immediately that if I calculate the roots of n of s, okay, that is solve b naught s power m plus b1 s power m minus 1 plus all the way till b of bm minus 1 s plus bm equals 0. Okay, the roots are called as, what will you call the roots of n of s as? So if you solve this equation, the numerator polynomial equals 0, right, and you get particular values of s, at those values of s, what will happen to the transfer function? It will become 0, right, because the numerator becomes 0. So the roots of n of s are what are called as the zeros of the transfer function. Okay, I hope it's clear why they are called zeros, right? The transfer function vanishes, right? So similarly, the roots of the polynomial P of s, that is, we solve a naught s power n plus a1 s power n minus 1 plus all the way till an minus 1 s plus an equals 0, right? The roots of P of s consequently should be called. So please note that at whatever values of s where the denominator polynomial, the roots of d of s, right? That's not P of s, sorry about that, right? So it's going to be d of s, right? The denominator polynomial. Okay, so wherever I have the denominator polynomial to be 0, right, you can immediately see that the transfer function becomes singular, right? So the transfer function is a complex function, right? Complex valued function in the variable s. S is a complex variable, right? That's something which all of us know, right? Now the point is, like if I have a complex function f of s, and in the s domain at certain points the function does not exist and its derivatives do not exist, those values of s are called as singular points or poles, right? We discussed it sometime before, right, when we briefly discussed complex variables, right? So consequently, the roots of d of s are called as the poles of the transfer function. Okay, so the denominator polynomials roots are what are called as the poles of the transfer function, right? So that's something which we should remember. Okay, yes.
So can you intuitively prove why n equal to n greater than m implies causality?
Causality. Okay, so let me give you a very simple example, right? So just to what to say convey that point. Okay, let's do it as an aside, right? So the question was, like how could one say that what to say n greater than or equal to m implies causality? Let me go the other way. Okay, I will show you how m greater than n will mean non-causality. Okay, let's do that way. Okay, so let's take a very simple case where y of t is equal to du t dt, right? So what are the values of n and m here? N is going to be 0, m is going to be 1, right? Do you agree? Okay, so here n is less than m, so we have gone to the other side, right? So now how is it anticipatory? A non-causal system is anticipatory, right? Why? Because what does the derivative do? See, suppose, like just to convey it graphically, right? So that we have a better idea, right? So let's say I plot u of t versus t, right? I give some arbitrary input, okay? But let's say I am at this instant of time, this is my current instant of time, t. So what does my derivative give me? It is a rate of change. Graphically, it will give me the slope, right? And the value of the slope. So in a certain sense, I will know what is going to come up in the future. So I am basing my output as the derivative of the input signal, right, which will tell me what is going to come in the future. So my system output is influenced at this instant of time, is influenced by what input will come in the next instant. So it tries to anticipate, right, and take action. So you can see that how it's non-causal, right? So if the output is going, if it senses that the input is going to decrease, the output will decrease, right? If the du dt, let's say we are at this point, if du dt is positive, the output will increase, right? If I am at this point where u of t has reached a maxima, local maxima, then the derivative will be 0, so output will be 0, right? So in a certain sense, it tries to anticipate what is happening. Okay, that's why it becomes non-causal. So now I hope you have an intuitive understanding of why this implies anticipation, right? Yeah. Okay, so what we will do is that, like, maybe what I will do is that I'm going to leave you with a few problems to do, right? And then we will come back in the next class and essentially discuss further, right? So let's look at a few exercise problems, right? So what I'm going to do is that, like, I'm going to essentially write down governing ordinary differential equations for a few simple LTI systems, right? And then you need to calculate the transfer function and get the unit step response. Okay, so that's the exercise I'm going to give you. Okay, or let's make life simpler. Okay, let's say we calculate the impulse response, unit impulse response. So you just need to take the inverse Laplace transform of the transfer function. That's all I want, right? So in each case, determine the plant transfer function. Okay, its poles and zeros, and calculate its unit step response. Sorry, unit impulse response. Okay, let's keep things simpler. Then we'll come to unit step response. Okay. Okay, so let me leave you with a few problems. Of course, the moment I say transfer function, obviously you should assume all initial conditions to be 0, all right. So okay, so the first problem is y double dot t plus 5y dot t plus 6yt equals 0, second order system. Second problem is y double dot t plus yt equals 0. Third problem is y double dot t plus y dot t minus 2yt equals 0. Okay, so for all the three systems, derive the transfer function, find the poles, zeros. Oh, sorry. Oh, okay, I can't have it as 0. Sorry about that. It should be u of t. Okay. I'm sorry. Yeah, please make the right hand side as the input u of t. Okay, sorry about that. Right. So derive the transfer function, find the pole zeros, and calculate the unit impulse response. Okay, we would start from here in the next class.